Can you hear me properly? I'm using my mobile data. I don't know what the problem is. I'm not able to connect to Microsoft Teams with the institute network. So I'm using my mobile data. Can you hear me properly?
Yes, ma'am.
Okay, so last time we were discussing the reference oscillator. We discussed how the reference signal, sinusoidal or square wave, can be generated. We basically discussed the theoretical principle. Don't think that these are the only elements that are present. There are many other circuit elements which we have not shown here. This is just a simple block diagram showing the major components. Okay. The oscillator is supposed to generate the reference signal at a particular frequency. The resonant frequency or some harmonics of the resonant frequency of the crystal. Okay. But there is nothing like an ideal oscillator. So although it is supposed to provide the signal, reference signal at a particular frequency, it always drifts. Therefore, the performance of an oscillator is measured by its accuracy and stability. Accuracy measures how well it is tuned to the desired frequency. So if its design frequency is 10 megahertz or 1 megahertz, then accuracy would measure how close the actual frequency is to the desired frequency or nominal frequency. Then stability measures how well it can operate at the designed or nominal frequency over a period of time. So here, an additional thing is that time is important. Over a particular period of time, its ability to operate at a particular frequency is measured by stability. Both are quantified by relative frequency deviation. However, there is a time period associated with stability, okay, which we do not have in case of accuracy. Both are quantified by the relative frequency deviation, capital F, which we already discussed towards the beginning. Capital F is equal to F minus F naught divided by F naught, where F is the actual frequency, F naught is the nominal or desired or design frequency, the frequency at which it is supposed to operate. So capital F is F minus F naught divided by F naught. It's called the relative frequency deviation. On the next slide, I will abbreviate it as RFD. Okay. Now, suppose a crystal oscillator has an RFD of 1 part per million. 1 part per million means 1 in 10 to the power minus 10 to the power 6, or we can say 10 to the power minus 6. The RFD is 10 to the power minus 6. So this can be interpreted as follows. Let's say the oscillator has a desired frequency of 1 megahertz, but it is actually running at a frequency 1 hertz less than 1 megahertz. So 1 megahertz means 10 to the power 6, and if you subtract 1 from that, you get this frequency. So although its design frequency is 1 megahertz, it is actually operating at this frequency. Then you just do this one, and the absolute value that you will get is 10 to the power minus 6. It can also operate at 1 hertz extra frequency. Then also we are interested in the deviation, absolute deviation. So we say that the RFD is 10 to the power minus 6. Now, since we keep track of time by counting the number of oscillations, any deviation in frequency from the desired value would reflect in time, right? It will result in an error in time as well. We prove the relationship between time error and frequency error in the class. We will not do that again. In case you are not sure how it can be derived, you need to refer to the lecture note. I think sometime in January when we talked about the overview of GNSS for the project purposes, there we talked about discussed the relationship between time error and frequency error, and I proved this equation. So delta t is the time error over some interval capital T. What is delta t? So delta t is actual time minus the time reported by the oscillator. So it is actual time minus the reported time of the oscillator. And it is the negative of f minus f naught by f, where f naught is the nominal frequency or design frequency. F is the actual frequency of the oscillator. Now let's assume that this oscillator is running fast, meaning f is greater than f naught. How will that translate to the time error? So f is greater than f naught. Our denominator is always positive, it is frequency. So this term is negative. Now capital T cannot be negative, right? So delta T is negative. Now delta T is actual time minus reported time. So this means the time reported by the oscillator is more than the actual time. Or in other words, the actual time is less than what the oscillator reports if the oscillator runs fast. On the other hand, if the oscillator is running slowly, the reverse happens. Actual time is more than the time reported by the oscillator. Because by design, it will always say, the oscillator will always say 1 second has elapsed when f naught oscillations are over. Okay, so whether f is more than f naught or less than f naught will eventually result in time error. And using this relationship, you can easily find out what happens to the time error when the oscillator is running fast or running slow. Running fast frequency is less than the desired frequency. Okay. Now, as I told you earlier, stability is associated with time. Now, there are two types of stability: short-term stability and long-term stability. Short-term stability is measured over a second or few hours in a day, whereas long-term stability is measured over a day, over several days, or over years. I have seen oscillators where the long-term stability is given over few years. So generally, the oscillator manufacturers keep both short-term stability and long-term stability. They report long-term stability over a few years, 3 years, 5 years, like also that also they can give the long-term stability. Okay, now why does the oscillator drift from its desired frequency? There are several factors. It drifts from the desired frequency due to environmental changes, for example, changes in temperature, pressure, humidity. They all affect the frequency, especially temperature. Temperature directly affects the frequency, can drift very easily if temperature changes. But pressure and humidity can also affect the frequency. Okay. Then after using the oscillator continuously for some time, its frequency can change. This is called aging. Mechanical vibrations can also change the frequency of the oscillator. So if the oscillator is mounted on a vehicle, of course the receiver will be on a the receiver is used on a vehicle. The vehicle undergoes some mechanical vibration. The oscillator will also be subjected to that, and that can change its frequency. This is why how the receiver is mounted on a vehicle which can vibrate largely is important. So mechanical vibrations can be reduced by mounting the receiver on an isolated platform with proper shielding, so that it does not get affected by the mechanical vibrations of the host vehicle. Okay. Now, There are some designs to correct the frequency error due to environmental conditions. Okay. In case of GNSS receiver, two such designs are generally used to compensate for the change in temperature. They are called temperature compensated crystal oscillator TCXO and oven controlled crystal oscillator OCX. So these two types of crystal oscillators are commonly used in GNSS receivers, TCXO and OCX. What is a TCXO? In case of a TCXO, there is a temperature sensor inside the oscillator, okay, and it senses the temperature. Depending on change in, so the oscillator is designed to operate at a particular temperature. But the sensor senses change in temperature, and depending on the change in temperature, a correction voltage is generated. Okay, this correction voltage changes some circuit elements. As I told you earlier, this is a very simplified block diagram. Okay, there are many other circuit elements that are also required. Okay. Now this beta is also determined by the crystal, which can also be represented as an RLC circuit, okay, resistor, inductor and capacitor circuit. There will be other elements as well. Okay, so when temperature changes, beta also changes. Okay. Now, depending on the change in temperature, a correction voltage is generated, and there are some circuit elements other than the crystal oscillator whose values can change depending on the voltage. For example, if there is a diode, particular type of diode, varactor diode, okay, and if you change the voltage to the diode, its capacitance changes. Okay, so by applying this correction voltage suitably, it is possible to change beta back to its original value. Okay, and the frequency can also be restored. The resonant frequency or the desired frequency can also be restored to its previous value. But this actually can work well within a narrow range of temperature change. Okay, it cannot accommodate a wide variation in temperature. The second one is much more robust. It's called oven controlled crystal oscillator. In this case, the oscillator is kept inside an oven whose temperature is maintained constant. Here we do not try to change the temperature. Rather, we try to take some corrective action based on the change in temperature. As a result, we can only accommodate for a fixed variation in temperature, a narrow variation in temperature. Whereas in this case, we do not do any corrective action based on temperature. We maintain the temperature constant inside an oven. Okay. So this is certainly better than the temperature compensated oscillator, crystal oscillator. But there is a downside. Since there has to be an oven, its weight is more compared to TCXO. Okay, price is also more. It is more expensive compared to a TCXO. And the warm-up time is more. Warm-up time is the time that the oscillator requires to give a stable frequency after it is turned on. So if you turn on an oscillator, don't think that immediately after turning on it will give you this reference signal at the desired frequency. It requires some time, and depending on the oscillator, it will be few seconds. Some manufacturers claim millisecond also, but there is a time needed for the oscillator to give a stable frequency. So that time is called the warm-up time. In case of the OCXO, the warm-up time is also more, but it gives better stability, better accuracy. Now here you can see the order of short-term stability for a TCXO. It is of the order of 10 to the power -8 to -9. That means over a second, short-term stability generally over a second or few seconds. So generally they say over a second. So over a second, the frequency error will be 1 part in 10 to the power 8. okay, or 10 to the power minus 9, the same way. Whereas an OCXO gives a much better short-term stability, 10 to the power minus 11. Long-term stability of the OCXO is generally 10 to the power minus 8, whereas for a TCXO it is on the order of 10 to the power minus 6 to minus 7. Okay. So here we have talked about the crystal oscillators. We know that GPS or GNSS satellites use atomic clocks. Atomic clocks are much more accurate than reference crystal oscillators, especially in terms of the long-term stability. They have much higher long-term stability. If the OCXO has 10 to the power minus 8 or minus 8, then in case of an atomic clock, it will be 10 to the power minus 13, minus 14 like this. So long-term stability of an atomic clock is much better than these crystal oscillators. But atomic clocks work on a completely different principles. They are the scale atomic clocks in receivers. Okay, but they are more expensive than TCX or LCX. So TCXO would cost a few thousand rupees, whereas an OCXO would cost few tens of thousands of rupees, say 30,000, 40,000 in rupees. And a chip scale atomic clock would cost few lakhs. Okay, but it can be expected that over the years, price would come down, and then the atomic chip scale atomic clocks would be used in receivers. But now that is not the reality. Some receiver manufacturers use, but most of them use TCX or OCX in receivers. Okay. Any question? If you are not able to hear me properly, if you have some problem, let me know. Okay. I do not know what you are hearing, how good my voice is, or whether you are able to see the screen properly or nothing. I know. So in case you find some problem, you should let me know. Is this fine?
Yes, ma'am.
Yes, ma'am.
Okay. So that's all about the reference oscillators. Next, we are going to talk about GNSS antennas. Since we are talking about the antenna in the context of the receiver, we will mainly concentrate on receiver antenna. But antenna, 1 minute. The antenna actually the same antenna can be used for transmission as well as reception, depending on how it is connected. Okay, so if it is connected to a voltage source, it will work as a transmit antenna. It can be used for transmission. If it is the same antenna is connected to some passive circuit elements, say receiver, it will work as a reception antenna. Okay. So whatever we discuss, whether it is in the context of transmit or receive antenna, the principles remain more or less the same. Okay. So since we are talking about the receiver antenna, here its objective is to convert electromagnetic radiation from satellites into electrical signals. We receive electromagnetic waves. The antenna converts the received electromagnetic waves into electrical signals. What is an electromagnetic radiation? Electromagnetic radiation is a synchronized oscillation of the electric field. The blue here shows the electric field and the magnetic field. The red shows the magnetic field, and they travel in a direction orthogonal to both of them. So you see along X you have the electric field, along Y you have the magnetic field, and they travel along the Z direction. Z is perpendicular to both X and Y. Here they are shown in vector form. This is the orientation of the electric field, this is the orientation of the magnetic field, and this is the direction along which both the fields propagate. So both the electric field and magnetic field are synchronized here. Later we'll see that the polarization of the electromagnetic radiation is important. A polarization actually is determined by the orientation of the electric field. If the electric field is fixed in space, it is called linear polarization. So as the waves travel, the orientation of the electric field does not change. It is fixed. If it is vertical, it is vertical. If it is horizontal, it is horizontal. Similarly, the magnetic field, because it has to be orthogonal. So if the electric field orientation is fixed, magnetic field orientation also has to be fixed. So if the orientation of the electric field is fixed in space, it is called linear polarization. Okay. Now, if it is vertical as seen by the receiver, then that polarization is called vertical polarization. If the electric field is horizontal with respect to the receiver, it is called horizontal polarization. Now, it is not necessary that the two fields are fixed in space. As the waves propagate, they can make some movement on this XY plane. If their amplitudes are fixed, if E and B have the fixed amplitude, and if they rotate in the XY plane, then that polarization is called circular polarization, because they make a circle together. They make a circle in the XY plane. Okay, that polarization is called circular polarization. Now, while rotating, if their amplitudes also change, then they will describe some ellipse. Okay, so that is a different polarization. Now, suppose the receiver is here, the observer is here. If he sees that the fields are rotating clockwise, so you just put some I here. So if the observer sees that the electric field is rotating clockwise, if the electric field rotates, magnetic field also has to rotate. Okay, so if the electric field rotates clockwise with respect to the observer, then that is called right-handed circular polarization. Then it's called left-handed circular polarization. You will understand why I am saying this on the next slide. But since I have this figure here, I can easily show you the polarization as the wave travels. That's why I am telling you this now. Now, when a polarization is right-handed circular polarization with respect to the observer, the transmitter would be here. So someone on the transmitter would see it as anti-clockwise. So right-handed circular polarization with respect to the receiver would become left-handed circular polarization. So it is important to mention with respect to whom you are saying it is right-handed or left-handed. Because if something is right-handed with respect to the observer, it becomes left-handed with respect to the transmitter. Okay. In this context, note that in case of GNSS, we have right-handed circular polarization. So if someone can see the electromagnetic radiation at the receiver level, he or she would find that it is right-handed circularly polarized. Okay. Now the question is how an antenna can convert electromagnetic radiation into electrical signal and vice versa. Convert electrical signals into electromagnetic radiation. So let's understand this without going into much detail uh, in the context of a transmitting antenna. So we'll see how an electrical signal is converted into electromagnetic radiation, and then from there we'll be able to understand how the reverse takes place. Okay. So let's first understand uh, in simple words, we will not go into much detail here, how the electromagnetic radiation is converted into how the electrical signals are converted into electromagnetic radiation. So let's first consider a parallel plate capacitor. This is a parallel plate capacitor and closed. It is shielded, put in a casing, and it is excited by an alternating voltage source. We are not going to use any concepts that you have not learned in your 10 plus 2. So all you need at this point is to recollect what you learned, some basic concepts of physics that you learned in your 10 plus 2. That's all. So a capacitor is excited by an alternating voltage. As a result, an electric field would be generated within the capacitor plates. But it is confined. The electric field remains confined within the plate, and an alternating current flows through the capacitor, right? And we know that if C is the capacitance, then I is the current and V is the voltage, then I is equal to C times dV by dt. That also you learned, I guess, in your basic electronic class or 10 plus 2. I is equal to C times dV by dt. Now let's consider this parallel plate capacitor, but remove the casing. Okay, and put the two plates vertically one after another in the same plane as shown here. Now the electric field between the plates would no longer be confined. The electric field would spread out in space as shown here. The same alternating voltage source is connected. Here also the current would flow through this capacitor plates, but the circuit is completed through space because electric field lines are completed through space. This is an equivalent representation. It has its own capacitance because the medium has changed. Earlier they were confined, now the medium has changed. This capacitance would be different from this one. But the same equation that relates current to voltage can be used. Now the difference here is that an alternating electric field, because we have connected our alternating voltage source, the electric field would also alternate, right? The difference between these two is that the electric field actually is spread in space. So we have an alternating electric field that varies with time, and current flows through the plates, right? Alternating current flows through the plates. Now, when an alternating current flows through a conductor, we know that it creates a magnetic field. It is given by Ampere's law. This also you studied in 10 plus 2. It gives a magnetic field. Any alternating current that flows through a conductor gives a magnetic field, produces a magnetic field. How can we find the direction of the magnetic field? For that, we have to use the right hand thumb rule. So we point the thumb along the direction of the current and curl all other fingers around the conductor. Then the direction of the curl will give the direction of the magnetic field. So here it is shown. So when an alternating current flows through a conductor, a magnetic field, alternating magnetic field is produced. So in this case, we have two fields, alternating electric field and alternating magnetic field. So this figure here shows the both electric field and magnetic field. Electric field is vertically up or down, and then magnetic field is horizontal. The directions are shown here. Next, so we have a conductor connected to alternating voltage source, and we see that alternating electric field and magnetic fields are generated. Next, we are going to apply a theory. It's called Maxwell's electromagnetic theory. We will not go into details of it. He has actually shown mathematically that this is possible. We are just going to use the conclusion that he derived from his analysis. He mathematically showed that when there is an electric field that alternates in time, it sends out a magnetic field into space. A traveling magnetic field is generated by a time alternating electric field. And then when we have a magnetic field alternating in time, it generates a traveling electric field that can propagate into space. So from an alternating electric field, we get a traveling magnetic field. And similarly, from an alternating magnetic field, oscillating magnetic field, we get a traveling electric field. And we know that in case of an electromagnetic radiation, we need these traveling waves, electric field and magnetic field, right? But here they should also be synchronized, right? Now this synchronization does not happen immediately after the in the vicinity of the conductor. This is basically an antenna. Okay, this is a simple form of antenna called dipole antenna. Okay, because it is polarized. But other complicated designs have the same basic principle. You have to generate alternating electric field and magnetic field, and that the alternating fields will send out traveling waves. This is the basic principle. But immediately in the vicinity of the antenna, the synchronization does not happen. Okay? It requires some distance for the two fields to become synchronized. So in the immediate vicinity of the antenna, they are not synchronized. This is called the near field. In this figure, they are shown to be synchronized for illustration purposes. For ease of understanding, they are shown as synchronized, but this synchronization does not happen in the near vicinity. It requires some distance for them to become eventually synchronized. So the region around the antenna where they are not yet synchronized, the traveling electric field and magnetic field are not yet synchronized, is called the near field. And the near field is followed by the far field. In the far field, they are both synchronized. So they travel as synchronized electric field and magnetic field. This is how an electromagnetic radiation is generated by a transmitting antenna. The same antenna can be used for receiving signal. How? Now in this case, we connected it to some voltage source. Instead of connecting it to some voltage source, let's say if we connect a passive circuit element, say a resistor or a receiver, okay? And let's say this antenna is sensitive to electric field. Then what will happen when the traveling electric field hits the antenna? It will generate an oscillating current, which will pass through that passive circuit element. So this way, a traveling electric field can generate an oscillating current, meaning you are converting electromagnetic radiation into electrical signal. Now, if the antenna is designed to be sensitive to the magnetic field, then the magnetic field will induce an alternating current. So basically, in place of such conducting rods, if you have coils, and the coils pass through this traveling magnetic field, then it will induce an alternating current. So by design, we can have an antenna to be sensitive to the electric field or magnetic field. Okay, if it is sensitive to the electric field, then the electric field, for example, in this case, if it experiences this traveling electric field, then the if it is connected to some passive circuit element, receiver or some resistor or something, then when the electric field hits the antenna, it will produce an alternating current. Hence, place of this straight conductor, if you have a coil, and that the coil experiences a magnetic field, the magnetic field lines pass through the coil, the magnetic field will induce a current. Okay, so this is how, by connecting the same antenna to a passive circuit, a receiver, basically the rest of the receiver, which does not have any source, alternating source, we can use it to receive signals. So that antenna will convert the electromagnetic radiation into electrical signal. If you do not understand something, ask me. Is this clear how, at least at a top level, how an antenna can be used for transmission and reception of signals? Are you following or you are not following? You have just joined and you do not listen to anything. I am only speaking. Is this the case? So should I assume that that is what is happening? You are not listening to anything? Have you understood or you did not understand anything? At least that much you can tell, right?
Excuse me, ma'am.
Yes.
Ma'am, we have both electric field and magnetic field. These two are combined with antenna. So my question is how the signal emits from the antenna and going to receiver.
Say that again.
Signal,
How?
like electrical signal and electric field and magnetic field both emits from antenna.
No.
Is there any phenomenon?
You are talking about a transmitting antenna or a receiving antenna? Which antenna you are talking about? I mean, which principle you are asking about? Transmitting antenna, yes. Yes, continue.
How the signal transmits from antenna? How it emits?
These traveling waves are generated. See, traveling waves can propagate in space, in a vacuum. Mathematically, this can be shown. Traveling wave means it will alternate in time, at the same time it will propagate in distance. So it has the equation will have two terms. One will be changing with distance, another will be t. So if you have a time alternating field, it just varies with time. If it also propagates in space, you will have a distance term associated with it. So theoretically, it can be shown that an alternating electric field sends out a traveling magnetic field. If you want, I can send you the derivation, but it is not possible to explain that in the class. In fact, if you search for Maxwell's electromagnetic theory, you will get to know. Mathematically, you will get some document. Of course, it has to be an authentic one. Otherwise, one should not rely much on the internet. From the source and the reference, one can make out whether it is an authentic one or not. Mathematically, it can be shown. Okay. And when you have a traveling wave means it is different. It does not only alternate in time, it also travels distance. That's why it's called a traveling electromagnetic field. An oscillating electric field creates a traveling magnetic field, Similarly, an oscillating magnetic field creates or generates a traveling electric field. This can be shown mathematically. Just think of a simple analogy. You throw a stone into a pond. So that is a disturbance, correct? And what that disturbance does, it propagates as waves through water, correct? So you throw a stone and that disturbance propagates as waves. It creates water waves, right? In this case, this time alternating electric field and magnetic field are disturbances. So these disturbances propagate in space as the electromagnetic radiation. The difference is that here you do not require any medium. In the case of water waves, you require water as a medium. Here you are actually propagating this disturbance as waves without any medium. It does not require any medium. This is how nature has designed it. Okay, and mathematically, if you want to know how this can happen, then you need to look for Maxwell's electromagnetic theory. Okay? Any other question? Shujit, are you there?
Yes, ma'am.
Or you are just done? So do you follow or you do not follow?
Follow, ma'am.
Okay. So we discussed that GNSS signals are right-handed circularly polarized from the receiver point of view. So if the receiver is where you are, you would see this as circular, right-handed circular polarization. The receiver would see this as right-handed circular polarization. Electric field and magnetic field are rotating clockwise in the XY plane. And the direction of propagation is perpendicular to the slide, away from the slide, pointing away from the slide. Okay. Now, why GNSS signals are designed as right-handed circularly polarized? See, if you have just linear polarization where it does not change its orientation. In this particular case, if you want the receiver antenna to have an oscillating current generated by this field, the antenna orientation should be this. In this particular case, the wave is propagating in this direction. This is the direction orientation of the electric field. If the antenna, receiver antenna is electric field sensitive, so you just put a conductor here. Only for this orientation, the traveling electric field would induce a current. If you change the orientation of the conductor, the electric field would not introduce any current. So only for a particular orientation of the antenna, you can generate the current, or you can convert the electromagnetic wave into electrical signal. But in case of GNSS, it is not possible to have a fixed orientation, depending on where you mount the receiver. If it is mounted on a vehicle which maneuvers, for example, on an aircraft, on a UAV, the antenna would not generate any signal, right? So you want something that would generate signals for any orientation of the antenna. Now just consider this case where the electric field is rotating as the propagation happens. Then for any orientation of the antenna, the electric field would induce current because the orientation is changing, correct? This is why GNSS signals have circular polarization. The amplitude do not change. Okay, just orientation changes, we get a circle, or they are circularly polarized. And we know that either it has to be right-handed circular polarization or left-handed circular polarization, either RHCP or LHCP. Now, by design, signals are RHCP. right-handed circularly polarized. How does it help? Now, suppose we know that signals can reach directly the antenna, or signals can get reflected and then reach the antenna. Now, suppose the signal gets reflected once and then reach the antenna. After a single reflection, right-handed circular polarization becomes left-handed circular. So RHCP becomes LHCP. When that reflected signal reaches the antenna, it actually becomes LHCP. Now the antenna is designed to receive RHCP signals. So whenever it experiences an LHCP signal, it rejects it. By design, it will not consider that. So this way, you can reject multipath. But if the signal is reflected twice, then again it becomes RHCP, right, and reach the antenna. But you should also note that after each reflection, it also gets attenuated. So after 2 reflections, it will be much weaker. Okay, although it will be received by the antenna, because it becomes RHCP, right-handed circularly polarized, it will be much weaker. So multiple reflections means it will be weaker. So this way, by having circular polarization, we can achieve 2 things. One is very important, both are important. For any orientation of the antenna, we can receive GNSS signals. We can also reject multipath to some extent. Okay. GNSS antennas are omnidirectional. So to understand what this means, let's first talk about an isotropic antenna and a directional antenna. Again at a top level. We are not going to discuss anything in detail. Everything is at a top level. If you listen to me, try to understand, you will understand it. But if you listen to me with some mental handicap that this is some concept of electrical circuits or related to electrical engineering, then you will never be able to understand. Because these are all simple concepts of physics, anybody can understand. So, what is an isotropic antenna? An isotropic antenna, actually an ideal concept. It does not exist in reality. It's an ideal antenna. An isotropic antenna is one which transmits power uniformly in all the directions. So let's say that power transmitted by an antenna is PT. Total power transmitted by an antenna is PT. Now imagine a sphere around that antenna. This antenna is not isotropic, it is directional. Okay. So just imagine a hypothetical antenna which transmits total power PT and it transmits power uniformly. Now, how can we say it transmits power uniformly? So for that purpose, imagine a sphere around that antenna. It's of radius capital R. So what is the surface of the sphere? 4 pi r square. The surface area is 4 pi r square. Now at any point on the sphere, you can find the power density or radiation intensity by dividing the total transmitted power by the area of the sphere. So in this case, PT by 4 pi r square. So anywhere on that sphere, the power density or radiation intensity would be PT by 4 pi r square when it is an isotropic antenna. That's why this dashed circle here is shown. Basically, the distance of the circle shows the radiation intensity or power density. Case of an isotropic antenna, it has the same radiation intensity or power density in all the directions. That's why it is shown by this dashed antenna, dashed circle. Okay. Now a directional antenna instead of transmitting power uniformly in all the directions, focuses more power in a particular direction by applying a suitable gain to the radiation intensity of that isotropic antenna. So an isotropic antenna would give the power density as Pt by 4 pi r square. Now to this you have to multiply this gain for the directional antenna. By shaping this gain properly, you can ensure that the antenna transmits signals only in a particular direction. So in this particular illustration, it transmits signals, electromagnetic waves or radiation only in this direction. Because in all other directions, this gain G is 0. So you take the power density of the isotropic antenna Pt by 4 pi r square. To that you multiply this gain. And this gain varies with directions. So in this case, it will focus power only in this direction. In other directions, you do not get. So if a receiver is here or here, it will not get any radiation from that antenna. Only if the receiver is here, it will get radiation. That's why it's called a directional antenna. Now here we defined it in the context of a transmitting antenna. Now the same antenna, if it is used for signal reception purposes, will receive signals only from this direction. Because it will apply the gain to the incoming radiation. And it will apply a high gain only when the radiation is coming from this direction. It will apply almost zero gain for radiations coming from other directions. So a directional transmitting antenna becomes a directional receiving antenna. Similarly, if you can have an isotropic antenna for reception of signals, it will receive signals from all the directions. Okay? But an isotropic antenna does not exist in reality. It is an abstract concept. Okay? An omnidirectional antenna is something that we can have between isotropic and directional. Okay? So it is said that an GNSS antenna is omnidirectional in azimuth plane. Now you will not understand what I mean by this. I will explain to you. What is an omnidirectional antenna? An omnidirectional antenna transmits or receives with uniform power in all directions perpendicular to an axis, but varying power at an angle to it. So you see, it is a combination of both isotropic and directional. This is the closest we can go to isotropic. We cannot have ideal isotropic antenna. We can have a directional antenna. This is something in between, because in one plane it transmits with uniform power. In other directions, the power varies, just like a directional antenna. So in a particular plane, it acts like an isotropic antenna, but in other directions, it is a directional antenna. Let's try to understand this in the context of GNSS. So let's say this is where the antenna is. This is the notation for the antenna. Okay, this is where the antenna is. And this is where the satellite is. So the line connecting the antenna and the satellite basically is the line of sight. Right? And this dashed vertical line here shows the reference line of the antenna. Okay. Now imagine a conic surface as shown here around this reference line, and this horizontal plane is the antenna reference plane. Okay, so this is the conic surface. Now if we project the satellite onto the horizontal plane of the antenna, it intersects here. To connect that projection to the antenna, we get this line. This angle is the elevation angle. We already talked about elevation and azimuth. Here we are defining the same in the context of the antenna. So this is the elevation angle. Okay. Now you choose some reference direction on the antenna horizontal plane. Just like this vertical axis, just pick some reference direction with respect to the antenna horizontal plane. Okay. Now this line makes an angle with that reference line on the horizontal plane. That angle is called azimuth. Just like the satellite azimuth and elevation, we are doing the same thing but with respect to the antenna. So this angle is the elevation angle, and on the antenna horizontal plane, if you draw some reference direction, with respect to that reference direction, this line of projection will make some angle. That angle is the azimuth angle. Now, see, on this plane, if you shift this point anywhere, you will vary the azimuth angle, right? The elevation is not changed, the azimuth is changed. Now just think of this base of the cone. If you shift this satellite along the periphery of the base, what do you have? You have the same elevation angle, but different azimuth angles. Just apply the apply the definition of azimuth and elevation. As you move the satellite along the periphery of the base, you vary azimuth, but you do not change elevation. Why? This angle remains the same. This angle is 90 degree minus elevation. This is the elevation angle. So for all the different position of the satellite along the periphery, you have the same elevation angle, but different azimuth. If instead of this position, if the satellite is here, the antenna will receive signal from this satellite, and it will apply the same gain. Okay, that's why it says transmits or receives with uniform power in azimuth plane. This is the azimuth plane because here azimuth only varies. Elevation is not changing along this circle. So you are actually varying azimuth, keeping the elevation constant. So in this case, whether the satellite is here, here, the antenna will apply the same gain while receiving signals from the satellite. Now imagine a vertical plane which contains this line and this vertical plane. So basically using this triangle, you imagine a vertical plane. So this vertical plane intersects this antenna horizontal plane along this line. It has a particular azimuth in this direction. So this is the right half of the plane. You just imagine a vertical plane considering this line and this. And then extend it on the other direction, here also. So for the right half of the plane, you have one azimuth. For the left half, you have another azimuth. Basically 180 degree minus the azimuth of the right half. Now you change the position of the satellite on that vertical plane. Elevation changes. So in this plane, the antenna will receive signals from the satellite with different gain. This is why it says that it receives with uniform power in all directions perpendicular to an axis. So in this case, that axis is this dashed vertical line. So just think of this plane, this circle. it will receive power, signal with uniform power. But varying power at an angle to it. You just think of that vertical plane and shift the satellite position on that vertical plane. Elevation changes. So it will receive signals from the satellite with different power as the elevation angle changes. So keeping the elevation constant, if you vary azimuth, the antenna does not apply different gain. It will receive power uniformly. But keeping azimuth constant, if you vary elevation, then it will not do the same. How the gain varies on that vertical plane that we just talked about, this line, and this line. Just connect and imagine a plane that contains these three lines, and then extend the plane on the other direction. So on this plane, how the gain varies? We know that the gain varies. The antenna will receive signal with varying gain on this plane. How the gain varies is shown here. This is the gain pattern. So imagine that vertical plane. On that vertical plane, if you change the satellite position, the elevation angle changes. Here, this is where the antenna is, and these radial lines are elevation angles. So when the satellite is here, for example, elevation is 0. So this point is mapped here. This point here is mapped here. When the satellite is at 90 degrees, it will be here. So this point is mapped here. The the radial line shows the elevation angles. So this right half corresponds to the right half of the vertical plane, and the left half here corresponds to the left half of the vertical plane. Okay? The concentric circles shows the gain that the antenna applies over that anisotropic antenna. So the gain of an isotropic antenna is 1. G is always 1 for an isotropic antenna. So whatever gain the antenna applies is actually the gain with respect to the isotropic antenna. And you just take logarithm of that gain, multiply 20. So that is what is shown here, dBi. I means with respect to isotropic antenna. An isotropic antenna has 0 dBi because G is unity. So log 10 will be 0 and 20 multiplies it will be 0. So this outer circle actually shows the gain of an isotropic antenna. And then as you reduce the radius of the circle, you get different gain. Okay? This blue line shows the gain for different angles, elevation angles. For example, when the satellite is at 90 degree elevation, gain is the same as that of an isotropic antenna. When it is at 30 degree elevation, this much gain is applied. So this is 0, this is minus 10. It will be somewhere in between, near minus 10, say minus 6 dB. I means with respect to isotropic antenna. At 60 degree elevation, this much gain is applied. Then at 0 degree elevation, this is the gain applied. Here it is between minus 10 and minus 20. So you can see that as the elevation decreases, it applies less and less gain. For high elevation satellites, it applies more gain. For low elevation satellites, the gain reduces. Here we have minus 10 dB, minus 20 dB, minus 30 dB. So this is certainly less than 0. So there are two things that we should note here. The antenna does not change gain when we vary azimuth, keeping the elevation constant. The antenna applies more gain to high elevation satellites. Why is it designed this way? Because you can have satellites at high elevation but at different azimuth on all the directions in the azimuth plane. And you want to give same importance to all the satellites. They are all high elevation satellites and you want signals from high elevation satellites. So why to differentiate them? Because they have different azimuth. That's why the antenna does not differentiate for different azimuth angles if the elevation is constant. But if elevation changes, you want signals from high elevation satellites. You do not want from low elevation satellites because there is a higher chance that those signals are reflected. Those signals are not so good. So at the antenna level, you attenuate them. This is why the gain is intelligently shaped this way. You give more importance to high elevation satellites and relatively low importance to low elevation satellites and attenuate to the extent possible for reflected signals. There is a higher chance that signals coming from bottom are reflected signals. So don't give high gain to them. So this way, by suitably designing the gain of the antenna, we can receive signals, good quality signals from high elevations angles and different azimuth. Okay. If you do not understand, ask me at this point. Don't think that this is explained on the internet or somewhere. And if I ask you how the gain pattern is designed this way, that answer you will not find anywhere. So if you do not ask me at this point, you will not be able to. So do you follow this or you do not follow? If you do not follow, I can repeat once. But let me know whether you follow it or not. You follow or not? If you do not follow, feel free to tell me. If you do not follow, feel free to tell me. Do you follow or you do not follow? Whatever I said regarding the antenna gain, do you follow or not follow?
I follow, ma'am.
Okay, Ajita, do you understand or you don't understand? Ajita is not there. It looks like Ajita has joined, but not there. I repeatedly asked you not to do this. Krishna?
Yes, I'm following.
Nilay? Nilay, do you understand? Nilay is also not there. Okay, Ajita has responded. Nilay? Looks like Nilay not there. Shujit?
Yes, ma'am.
So do you understand why the gain pattern is shaped this way? Why we have more gain for high elevation and low gain for low elevation?
Yes, ma'am.
So Ajita says she could not see some of the slides. How about others? Is this a problem at my end? Could you see all the slides that I had shown?
Yes,
Yes,
ma'am, we
ma'am.
can see.
Yes, ma'am.
Neela is not there. It looks like Neela is not present. It's better not to join this way because I will not give attendance. So let's take a 5-minute break now. We'll continue after the break. Now, whatever I am discussing, you will not find anywhere, okay? The way I am discussing, you will not find anywhere. Uh, so if you do not follow something, you need to ask me. Otherwise, if I ask question, you will not be able to answer anything. Asking question is one thing, but you have registered for the class, you should at least learn something. Uh, okay, let's have a 5 minute break and then we'll continue. So it's 12:21. We'll resume our discussion at 12:26. So let's continue the discussion. So all three are there. If all three are there, then I'll.
Yes, ma'am. Ma'am, Neelay just texted. He said he's traveling, so he's having a bad connection.
Yeah, I saw that. Shujit and Ajita, are you also there?
There, ma'am.
Yes, ma'am.
Okay, then I'll continue. Now, GNSS antennas are sensitive to signals over a band of frequencies. Okay, so suppose you have an antenna that is designed to receive signals in the L1 band, meaning the carrier frequency is 1575.42 megahertz, and the antenna will receive signals over a band of frequencies around this carrier frequency. Let's say some 10 to 20 megahertz we consider around this. So antenna will be sensitive to all the signals within this band around that carrier frequency. Okay, this is called the antenna bandwidth. Now an antenna can also be designed to receive signals in multiple bands. For example, you can have a GPS IRNSS antenna which can receive signals from both GPS and IRNSS satellites. So GPS has different carrier frequencies: L1, L2, L5, 1575, 1175, 1227 MHz, different carrier frequencies. So it will receive signals over a band around these three carrier frequencies. Then IRNSS has two bands, L5 and S. So an antenna can be designed to receive signals over multiple bands. Each band has a corresponding carrier frequency. But such an antenna would not be a small antenna, because if you consider L5 and S, L5 is 1175 and S is 2492 megahertz. There is a large separation. Okay, so the antenna which is designed to receive signal from GPS as well as an INS at present uh, is not a small antenna. It's a relatively large antenna. Okay. But if you want to have IRNSS in cell phones, you need a small antenna. Okay. Probably this is one of the motivations why ISRO decided to have another frequency in the L band for new IRNSS satellites, L1 band. So new IRNSS satellites will have L1 in addition to L5 and S. Okay. So there is a small separation between L1 and L5. GPS has L1 and L5, and GPS antenna, small antennas on the phone can receive both L1 and L5. Some of you had shown L1 and L5 both. Okay. So an antenna can receive signals in multiple bands from multiple constellations. Now, where the antenna is mounted, especially if it is a maneuvering vehicle, is important. It should be mounted in a place where it can see the sky clearly. So a suitable place would be vehicle roof. In case of an aircraft, antenna is GPS antenna, GNSS antenna is mounted on the top of the fuselage. Okay. So antenna has to be mounted outside on the roof. But other receiver components cannot be kept outside. They are all sensitive electric components. They have sensitive electronic equipment components. So they cannot be kept outside. So the rest of the receiver is kept inside the vehicle, whereas the antenna is mounted outside the vehicle. So there is a cable, antenna cable, that connects the antenna to the rest of the receiver. The antenna converts electromagnetic waves to electrical signals, and the converted electrical signals travel through the antenna cable to reach the rest of the receiver. Okay. Now the signal hits the antenna at some time. That is actually the time of reception. But the signal requires, if converted electrical signal requires some time to pass through the antenna cable and reach the rest of the receiver where actual processing, signal processing takes place. So there is a cable delay, transmission delay. And this delay fortunately is the same for all the signals, all satellites. So when the receiver estimates the receiver clock error, actually this transmission delay is included in the receiver clock error, because just like the receiver clock error, which is common to all satellites, this delay is also common to all the satellites. So the estimated receiver clock error will also have a component coming from the cable delay, antenna cable delay. Now some receiver manufacturers provide a provision to correct the receiver clock based on the estimated receiver clock error. In that case, if you do not remove the antenna cable delay, it will wrongly correct the receiver clock, because the estimated receiver clock has not only the actual receiver clock error but also the cable delay. Now the length of the cable is known, okay, it can be precisely measured, and the cable delay is proportional to the length of the cable. So the cable length can be measured and the cable delay can be precisely obtained in advance. Then from the estimated receiver clock error, this cable delay component can be removed, and the remaining part can be used to correct the receiver clock. Without that, it will wrongly steer the receiver clock. Okay? So if the manufacturer opts for correcting the receiver clock based on the estimated clock error, he or she has to compensate for the cable delay. Okay. Now see, an antenna is a distributed body. Electromagnetic wave hits the antenna. Antenna converts the electromagnetic radiation into electrical signal. Finally, receiver determines the position. Position can be of a particular point, right? It cannot be of a distributed body. Even if it is a distributed body, you have to select a particular point. So for which point the position is given by the receiver. The receiver determines the position of antenna mean phase center, which need not be located on the antenna. It can also be located in space. What is that mean phase center? To understand what mean phase center, we need to go back to antenna operating principles again. So let's assume that we have a transmitting antenna. So antenna produces alternating electric and magnetic fields. So let's say this is the near field of the antenna. Traveling waves are generated, but traveling waves are not synchronized completely. And then from here the far field starts, where the traveling electric and magnetic fields are synchronized. Okay, and let's assume that we have an ideal antenna. In case of an ideal antenna, when the electric field and magnetic field are synchronized, it can be shown that they propagate as these spherical fronts from a point which is at the center of all these concentric spheres. You imagine it in 3D, so they will become spheres. This is the case in case of an ideal antenna. Now what are these contours? They represent spherical contours, but what exactly they are? So you just take multiple points on a contour. They all have the same electric field and magnetic field. So let's assume that we have this point and this point, 2 points at different orientation in space. Now if you consider the electric field and magnetic field, so they propagate in all the directions. Now for these 2 points, the electric field and the magnetic field will have the same phase. So say point 1 has this electric field, point 2 also has the same electric field, same phase. The same goes for the magnetic field also. So they are actually equiphase contours. So all the points you just take, so you consider the propagated electric field and magnetic field in all the directions. So there are some points in space which will have the same electric field and same magnetic field, correct? So you connect those points. And in case of an ideal antenna, this will be a sphere. You get spherical contours. These are also called equiphase contours because all the points here will have the same phase. Whether you take electric field or magnetic field, corresponding phases will be the same for different points. So in case of an ideal antenna, you can see that the equiphase contours are perfect spheres. Now think of from the point of view of a receiving antenna. In case of the receiving antenna, suppose it is an ideal antenna, it will see the receiving electromagnetic waves this way. These are all equiphase contours from a receiver antenna point of view. Perfect spheres. Okay. Now for a receiving antenna, the phase center is the point where the electromagnetic wave is converted into electric signal. In case of an ideal antenna, it will be just a single point. So after this point, you don't have any electromagnetic radiation. You again have this alternating field, electric field. If it is an E-field antenna, sensitive antenna or M-field sensitive antenna, you get an alternating current. And if it is a perfect antenna, ideal antenna, this is just a point. Okay, it is as if it captures the electromagnetic radiation and converts it into electrical signal. Okay, this is the case for an ideal antenna. In case of a real antenna, the equiphase contour will be something like this, not a sphere. The same contour, which is a sphere here for an ideal antenna, would be somewhat like this. Some representative diagram. Okay, don't think that it will be like this always. So it will not be a sphere. This is an equiphase contour. So you take two different points and find their phase. They will have the same phase, same electric field phase, same magnetic field phase. But it is not a sphere. Okay. Now we need to find the mean phase center. Now we don't have a point. We don't have. How can we find the mean phase center? So we fit a sphere to this irregular shape. A sphere is fitted in such a way that the error is minimized. So this is the error. Right? You consider all the errors in all directions, square them, sum them up. So that is the mean square error. The sum of the square of errors. Okay. And this sphere is fitted by minimizing that sum of the square of error. Okay, and then the center of that fitted sphere, globally fitted sphere, is the average mean center or mean phase center. The receiver determines position of the average or mean phase center. Okay. Now don't think that it will be fixed. See, the receiver determines position based on signals from satellites. It's not possible to receive signals from satellites in all the directions. In some time instant, it may receive signals from satellites, say from these directions, and then it will give the position. So in that case, you just feed the sphere only partially, and the center of that fitted sphere will be the average phase center or mean phase center. For some other time instant, it can receive signals from some other satellites at other elevation and azimuth. Then the average phase center will be located somewhere else. So the average phase center not only will be in the space, it can also change its location depending on which satellite signals you receive. Okay? Any question? If you do not have any question, then I'll move to the next topic. Okay. Here I had shown the 6 primary blocks of a receiver. Antenna we already discussed. Receiver clock we discussed, mainly the reference oscillator. We did not talk about the synthesizer. Synthesizer basically has electrical circuits to scale up or down the frequency, the reference signal generated by the reference oscillator as needed by different blocks. The next component or the primary block that we are going to discuss is the front end. We will not be able to complete this today, but we'll start and the rest will complete in the next class. If you have any specific questions about antenna, reference oscillator, something that you could not follow, you can ask me now. Otherwise, I'll move on to the next block, which is the front end. So in this presentation, we are going to talk about receiver. Let me see, here we have front end, then baseband signal processor, then ranging processor. In the next presentation, we'll talk about the front end, baseband signal processor, and partially the ranging processor. Ranging processor requires a little more detailed discussion, so part of it will be in the next presentation and the rest will be in the next presentation. So today we will not be able to complete all this, we will just start and the rest will be completed in the next class. Okay. This is a typical front end configuration. If you are not familiar with these terms, don't get panicked, okay? I am going to explain all of them in simple words. You need not worry about this, okay? Just be a little patient and open to learning something new in case you are not familiar with this. So this is a typical front end configuration for CA code. Okay, this is shown for CA. We are considering only CA code processing. The simplest of all codes is the CA code. An open service, standard positioning service or open service for the civilian users. This is a typical front-end configuration for CA code processing. And of course, this is representative. Don't think that all the receivers use this configuration for processing CA code signals. CA code processing means signal, carrier signal which has CA code, which is modulated by CA code. We are considering only that part. This is just a representative diagram, okay? And we are going to understand the principle of a receiver front end with the help of this. What does a front end do? A front end performs 4 tasks. We know that signal is very weak when it reaches the antenna. So it has to power amplify the signal. Noise is also included. At this point, we cannot differentiate noise from signal. So the front end basically amplifies the power of both signal and noise. This is one task. Second task, in the earlier presentation, I said that antenna has its own bandwidth. That will be around 10 to 20 megahertz around the carrier. But we cannot allow to have such a large bandwidth depending on what you are processing. If it is a CO code processing, such large bandwidth is not desirable because it introduces more noise. Higher the bandwidth, more will be the noise. We want to eliminate noise. At the same time, we do not want to lose important information from the signal. So we need to narrow down the bandwidth. The front end narrows down the bandwidth. The third task that it performs is down conversion. What is down conversion? We know that the carrier is in the gigahertz level. And we want something at a lower frequency because gigahertz level processing means you need more resources. A single chip, simple chip, small chip cannot have many resources, right? So with low resources, we should be able to get comparable performance. That is achieved with the help of down conversion. It down converts the gigahertz frequency to megahertz. This is the third task performed by a front end. Fourth is signal is in analog form. We cannot process analog signals. We have to eventually digitize it. The digitization, analog to digital conversion is done at the end. So after the front end, all processing is in digital domain. So it has four tasks. Amplifies the power of signal plus noise because signal is very weak. This power is on the order of 10 to the power minus 14 to minus 20 watts. Without amplifying, noise level is also low, but signal is even lower. And no circuit can process such weak signals and noise. So the front end has to amplify the power. Then narrowing down the bandwidth with the help of bandpass filter, down conversion, converting gigahertz frequency to megahertz, finally analog to digital conversion. So these are the four tasks performed by a front end. Now let's see how they are performed. We are not going to discuss the analog to digital conversion in more detail. We'll just note that there is a block at the end of the front end, native D converter, analog to digital converter, which performs that job. It converts analog signal into digital form. Now the sampling frequency is important. At what frequency it will generate the samples? That depends on the null to null bandwidth of the code. We discussed null to null bandwidth. Now if we do not want to distort the signal, the sampling frequency should be at least 2.5 times the null to null bandwidth. This is a rule of thumb. It should be at least 2.5 times the null to null bandwidth. Sampling frequency is important. Okay. Then these two stages are actually down conversion. We'll come to down conversion in more detail on the next slide, but note that the down conversion here in this configuration is done in two stages. So let's say we have L1 frequency 1575.42 megahertz, which is about 1.5 gigahertz. And we want to down convert it to some megahertz. Instead of doing it in one stage, modern design can also convert gigahertz to few megahertz, but generally it is done in two stages. That is what is shown here. So this stage we will down convert it, say from 1.5 gigahertz to say some tens of megahertz. Okay, and then the second stage will down convert it further from some tens of megahertz to few megahertz. It depends on the design. Okay. what frequency they will down convert it to. Now the frequency to which it is down converted is called intermediate frequency. So this will be intermediate frequency 1, IF1, and this will be IF2, intermediate frequency 2, or the final intermediate frequency. We simply call it intermediate frequency. Okay, we'll come to the down conversion stage later. Now, other than down conversion, we also have amplifiers to amplify signal plus noise power and some band pass filters. Spread. Now, see how much the power has to be amplified. In the last class, I mentioned that about 100 dB. 100 dB means how much? 10 to the power 10 times. So you just do log 10 of 10 to the power 10 and multiply 10 outside. You get 100 dB. Because 10 to the power 10 means you get 10 outside and you already have 10. So 10 will be multiplied with 10, 100 dB. So 100 dB power amplification means 10 to the power 10 times you are amplifying the power. If you want to do it with just one amplifier, it would pose a significant design challenge. See, just imagine this side you have power, input power, and this side you will have, if you want to do it with a single amplifier, this side you have power 10 to the power 10 times. By any means, so gain is 10 to the power 10 times, power is simplified by 10 to the power 10 times. By any means, if this signal, part of this signal is leaked through the circuit, this side, it will be amplified 10 to the power 10 times and result in an oscillation load. So to avoid any leakage, you have to insulate things. Design becomes significantly challenging. This is why this amplification is distributed in stages. So instead of amplifying it by 100 dB at one go, power amplification is distributed in stages. Here we see 20 dB immediately after the antenna, then 40 dB, 20 plus 40, 60, and then here another 40 dB, 100 dB. So this way 100 dB gain is distributed instead of having just one amplifier with 100 dB. Okay. But you see that this amplifier is a little different from the other two. It is noted as the low noise amplifier, LNA, low noise amplifier. It not only amplifies the signal power, it also introduces low noise. See, whenever a component, a circuit component processes signal, it introduces its own noise. There will always be some noise introduced. It will be generated internally. It's called thermal noise. So whenever a circuit element is processing signal, it will generate some noise and that noise will be added. Okay. Now we want to design the component in such a way that the noise addition is as minimal as possible. Right? But there are other constraints as well. If you want to reduce noise, you have to use sophisticated design. Price would go up. So many other design considerations you need to take into account. It can be shown that mathematically there is a formula which shows that how much noise is added by a block is determined by the gain of the preceding block. So if this block has a very high gain, the noise added by the subsequent blocks would be small. It can be shown mathematically. Okay, don't think of any physical explanation or anything. It is mathematically determined that the noise that would be introduced by this, the overall noise, you need to calculate the overall noise level. In the overall noise level, it can be shown that the noise that is introduced by a particular block is attenuated by the gains of the preceding block. So if you consider this one, you need to consider both. This does not have any gain. It has a gain. So if this gain is large, the noise that would be introduced by this block would be small. And the same goes for this one. For this one, you have 40 dB, you have 20 dB, 60 dB gain. So noise introduced by this block would be even smaller. But how about this one? This does not have any preceding block that would give a high gain. So this has to be specifically designed such that it introduces low noise. Other blocks, other amplifiers need not be low noise because automatically, mathematically it can be shown that their noise would be attenuated by the gain of the preceding block. We are actually interested in the final noise level. So, and each component will contribute some noise to the final noise level. That noise contribution would be attenuated if the preceding block has a high gain. So this holds for all the subsequent blocks, not for this block. So this has to be specifically designed such that it introduces low noise. This is why it's called a low noise amplifier. Okay. Now an amplifier amplifies signal power. While doing so, it introduces noise. It also generates some unwanted signals called spurious signals. We do not want this byproduct. We just want the power amplification. So the spurious signals are noise that are generated by the amplifier can be removed using a band pass filter. So any amplifier is always followed by a filter. You see this one, it has a filter. This amplifier has a filter. This has a filter. So always an amplifier is followed by a filter so that this byproduct can be removed. Okay, now what is a band pass filter? Here we see band pass filters. BPF, 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 BPF. In case you do not know, a band pass filter passes a band of frequencies around the center frequency. Here you see the amplitude of the transfer function of the band pass filter. It looks like this. So this is the center frequency. The gain is maximum here, and then the bandwidth is the pass band is the range of frequencies over which the maximum gain falls 3 dB below the 0 dB value. The gain falls 3 dB below the maximum gain. So this is the bandwidth. So any signal that has frequency within this band will be passed by the filter. If it lies outside its pass band, then it will be attenuated, it will not be allowed. So outside this band, its amplitude falls off sharply. Within the pass band, signals are allowed. Outside the pass band, signals are not allowed. These are called stop bands. Only this is the band which will be allowed by the band pass filter. Okay, outside this range, no signals will be allowed. Now the center frequency is important. See, here we have 1, 2, 3, 4, 5 band pass filters. They have different center frequencies. In this case, it is the carrier frequency 1.575 gigahertz is the center frequency, and its pass band is 50 megahertz. Here also it is the same 1.5 gigahertz. I'll just note this and then stop. At this point, it has been down converted. So this will not have center frequency at 1.5 gigahertz. It has to be at the down converted megahertz frequency. So its center frequency is different. This will be at the same in down converted frequency. Again, second down conversion happens, and this filter will have the final intermediate frequency as the center frequency. So the filters need not have the same center frequency. Depending on where they are placed, they have different center frequencies. And also note how the pass band is changing. 50 megahertz. So in this case, the antenna bandwidth was more than 50 megahertz. 50 megahertz, then 30 megahertz pass band. Finally, here it is 3 megahertz. This is also 3 megahertz. This band pass filter is required because we do not want unwanted signals. And later we'll see that before down conversion, a band pass filter is required. So it does not changes the pass band, but it is required for other reasons. This one reduces the pass band further 2 megahertz. Now we are considering only CA code. CA code has null to null bandwidth of 2 megahertz, 2.046 megahertz. So roughly it is shown 2 megahertz. So pass band can be 2 megahertz. You cannot go below 2 megahertz. If you go below 2 megahertz, you will distort the signal. So it should be at least the null to null bandwidth or more than that. Okay, but it should not be below the null to null. And the sampling frequency must be at least twice or 2.5 times of the pass band of this. So if you consider 2 megahertz, it will be 2.2 times to 2.5 times of this 4 to 5 megahertz at least. The sampling frequency has to be chosen. Okay, that's all. We'll continue tomorrow. Sorry, next week, next Wednesday.